Hi, good to see you guys back. I guess you had your second term examinations and are now set to move into the third term after, of course, the holidays. I've kind of tried to keep in pace with the flow that your teacher may be following. But of course, there are going to be slight differences depending on which school you are and so on and so forth. So I think we last covered about light, which was a kind of energy. And today I'm going to speak to you about sound, which is another form of energy. Light is an electromagnetic wave, so in some sense, it is a combination of electricals and magnetic energy synchronized together. But sound is a purely mechanical concept, really, and is a part of really mechanical energy. We call it out separately because it's so impactful and useful to our lives, and we kind of hear about it or speak about it literally. So, what does sound really mean? I think one of the key parts of sound, I think, is best to analyze using some kind of a musical instrument. The reason I'm calling out a musical instrument is, for example, if you take a instrument like the violin or the veena, or a percussion instrument like the tabla, you do get very pure notes. A musician can play very, very clear notes depending on which string is plucked. Each string represents a particular type of sound. It's difficult to express it, but if you just get hold of a violin or a veena and pluck each string separately, you will realize that each one is a little different from the other, and you can distinctively decipher the difference between the sound. So essentially, sound is really a mechanical wave that emanates from the source, like the string, and comes up to your ear, where there is a eardrum which vibrates and you get a sensation of sound. The key parameters that qualify a particular type of sound is really the frequency. For example, in a string instrument, if you were to pluck the string, you can see that the string is moving and coming back and forth and vibrating. The number of vibrations that the string makes in a unit time, typically a second, is called its frequency. So the number of vibrations per second is the frequency of that particular sound, and its unit is second inverse, but there's a more evolved unit that is usually used, and hertz. Hertz is the SI unit for frequency of sound, and is essentially the number of vibrations per second or second inverse. Since there is a element of time within the vibration, you can also kind of measure the time that it takes for a vibration. So in some sense, if you were to looking at one extreme that the string goes to, and you count the time that it comes back to that time, to that position, or if it is at a relaxed position, it goes one way to the extreme, goes the other way to the other extreme, and then comes back to the original position. The time taken for that vibration is the time period. And essentially, frequency and time periods are reciprocals of each other. So time period will be measured in second, frequency in second inverse, and therefore called hertz. But how much it moves away from that central position, let's say you pluck the string away, how far away you move it and leave it, and then it continues to move away from the central position, is called the amplitude. And that's essentially an effect of distance. How much does it move from its central position? So all sound waves can essentially be characterized by either a frequency or time period, which are just reciprocals to each other, and of course the amplitude of how much it moves. But that simply does not sum everything that we know about sound. There is how loud the sound is. You can clearly make out when someone is hitting a drum softly versus very, very hard. Obviously, if it is very, very loud, you just call that it is very, very loud, and that's measured in decibels. How loud a particular sound is. Something like 80 decibels is definitely very, 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 very loud. and but it can also be very soft. So we can hear about something from about 10 decimals all the way to 150 decimals, but anything above 80 would typically be quite damaging, especially if it's a long hours of exposure to that kind of loudness. The other thing is a sense of pitch. Musicians will sing songs at various, or if you look at the voice of singers, you will see that some voices are shrill and some of them are hoarse. Typically, a woman's voice would be more shrill, and a man's voice would be more hoarse, and those are essentially sort of like the pitch, which is kind of related to the frequency. But even if the loudness and pitch of two musical instruments are same and you make a pure sound, you still know that they are from two different types of musical instruments. And therefore, that's called the quality of sound. The quality of sound will differ depending on not just the string, it depends on what's the kind of acoustics around the string. For example, you see a guitar, it has a acoustic box right where you strum. And similarly, a veena has a very different way to magnify the acoustics that flow through the instrument. In fact, even our voices, while we almost have vocal cords very similarly, the sound that emanates from the throat and while it comes out to the mouth, and mouth is really the cavity which is resonating the sound that's coming out from the vocal cords, will be different. And therefore, because we have different mouth shape, different lip shape, different ways we swirl our tongue while speaking, the voice is distinctly different between each one of us. You could virtually voice fingerprint as you can, and that's that quality of sound. The other aspect of sound is simply to do with frequency. So the human ear can hear something between 20 hertz to 20 kilohertz in frequency. The human ear is responsive to that sound. I call it human ear because there are dogs which will respond to frequencies higher. There are also animals that can respond to frequencies lower. So anything lower than 20 hertz is called a subsonic, and anything greater than 20 kilohertz, which is 20,000 hertz, is ultrasonic. That's typically called out that because that's really not in the human range of frequencies. But they are sound waves too. And just like the sound you can hear, they are mechanical waves, pressure waves, oscillations transmitting through any medium. There are also from light, other than the fact that there are very distinct different types of energies, one being electromagnetic, this being purely mechanical, concepts such as reflection and refraction hold true. So sound will get reflected around a wall. The reason that you can stand behind me and still listen is because the sound is going forward, hitting a wall in front of me and coming back to the person. In fact, it does multiple reflections, and therefore when I speak, I really don't have to look towards the person I have to speak, but the sound is generally heard. It's also true that refraction happens in the same way. There will be but there's something more important which did not get covered when I was speaking about light, which is the diffraction of light. So while refraction is bending of light when it goes from a medium to a denser medium because the media is changing, diffraction is a concept where a wave bends around the edges that it sees. For example, if I'm sitting here, there's a door. Around the edge of the door, when the door is open, the bending of light is called diffraction, and the bending of sound is also called diffraction. It isn't called out very much in light because the diffraction is amount by which it gets diffracted is very, very small. A little example that I can tell you is from my school days. We had, when we were sitting in the classroom and being the bunch of noisy kids that we used to make a lot of noise. But we could hear distinctly when the principal started walking on the corridor, because he was an army man, a retired army man, and he wore really the army regulation boots, and his boots would creak because it would kind of make it characteristic sound. And while we would never be able to see the corridor because the corridor was obviously blocked off by the walls from the classroom, but we could hear him. And of course, we would all go silent. That's simply because light does not diffract enough around a wall, and therefore the wall, the opaque wall, you can't see through the opaque wall. Whereas sound kind of come through, and when it sees the door, it wraps itself around, because sound can very freely bend around walls. And that's why sitting in one room, you can pretty much shout out in your house and have other people listen to you while they still can't see you. So diffraction then becomes fairly important, somewhat also related to the wavelength. Sounds have much larger wavelengths, which is, if it's a wave, the difference between the low pressure to low pressure, or from crest to trough, is what is defined as a wavelength. I wouldn't spend too much time, because there isn't much call out on wavelengths and so on in your book yet. But that's what leads to diffraction, and diffraction becomes very important for sound. The places where you would use one of these properties, is reflection, refraction, or diffraction, is in the concept of echo. If you have gone to a kind of a mountain and you shout out, let's say you say hello, and you hear back hello after, of course, a certain amount of time, that's essentially because the sound, as it travels out, and because there is no obstacle near you, and the nearest obstacle is probably a faraway mountain, the sound travels to that mountain, gets reflected on that mountain or that obstacle, and comes back to you distinctly. If that sound comes back later than 1/10 of a second, your ear can pick it up as a different sound, and therefore calls it out an echo. And it's called 1/10 of a second simply because there's something called the speed of sound. It has to go far away and come back, and the distance will kind of say how much time will it take to come back. So if it's beyond 1/10 of a second, then you will see it as a different kind of a sound. In normal speaking, you don't hear echo, simply because the walls are so close by. Even if it reflects and comes back, it comes back within that 1/10 of a second, and your ear doesn't pick it up as a distinct sound. But whereas in a large auditorium, for example, you would hear an echo. Imagine a movie hall, which is of course very big, and typically the distance for sound to travel that is within that 1/10 of a second is about 17 meters, and the theater is obviously bigger than 17 meters, so usually about 50 to 100 meters. You're watching a movie and you kept hearing reflected sounds, obviously it's going to be very, very distracting. So how do they take care of in a very, very large hall? So one of the things to do is, if sound hits the wall and reflects back, of course you will get an echo. But if you're able to kind of, just absorb the sound into the wall and not allow it, the reflected wave, to get generated, you would avoid the problem of echo. And that's why if you look at cinema theaters, you see all the walls are paneled with cushions and leather cushioning and so on, or even with soft boards, that sound simply get absorbed into that material, and the echo doesn't come back to you. So that's absorption, which is also an important characteristic of a material in interaction with the wave. So absorption, we spoke about it in terms of light too, and even in sound, absorption becomes similarly important. But the concept of echo can also be used for measuring distances. So if you made a sound through an instrument, and you knew that it has to go somewhere and come back, and you measured the time lapse, and knowing the speed of sound in the medium, you could, with the time gap, you could easily predict what's the distance at which the reflector is. So that's used in something called a sonar, which is used in ships to simply measure the depth of the sea. So the sonar kind of sends out a beam, ultrasonic beam, into the ocean floor. It hits the ocean floor and comes back. You know that it's come back, let's say, after a certain time in seconds. You know that the speed of sound in water, and therefore you calculate what is that distance traveled. Of course, half the distance will be the depth of the seafloor. We spoke about speed. Speed is simply the distance traveled by the wave in a given time. So if I stand here and I shout out to my friend who is 100 meters away and I signal when I shout, and he's able to see my, let's say, signal, and then looks at how much later he's able to perceive that sound, that time by the distance would be obviously the speed of sound. And we know the speed of sound in air, and it's calculated and reported well, is about 332 meters per second. It's faster in water, which is 1500 meters per second. And it's much faster in steel, which is 4500 meters per second. Because it's a mechanical wave, it really uses the density as a concept, because mechanics, is strongly dependent on density of how much material is packed in a given amount of volume. Therefore, as the material becomes denser, it's more effectively able to transfer energy, in this case sound, and therefore the speed of sound is 4500 meters per second in steel, as against something like air, which is not a very dense material. The fact I can move things around, my hands freely in air, because air is not a very dense medium. I imagine trying to do this underwater. Obviously, water is more dense, and then you realize the speed of sound in water is about 5 times what you can do in air. So, in some sense, that was all the concepts around sound, which is very similar in some ways to light, but also very different. First of all, just by nature of being completely different types of waves in their genesis, and of course in the properties that it exhibits. I think this is itself a very fascinating field. The study of sound is essentially acoustics. You see the amount of energy that is spent, in developing and engineering products that produce sound, whether it's an instrumental quality or whether it's in more recent sound speakers. So the fact that you can buy a speaker for 2000 rupees and all the way up to a few lakhs is simply because the engineering of the acoustics is challenging, and therefore the materials, the choice of design and so on end up in giving you a very, very high fidelity of the original music that's composed and played through those speakers. And similarly, and not to take away from the artisans who make something like a flute, a piece of bamboo fashioned in a particular way is of course amazing on how clear notes can be produced from simply a piece of bamboo in a flute, or for that matter just by a few strings tied together. I remember the kind of first sound experiments that we really did as boys was to tuck in a piece of blade in those days between two planks of wood on our desk and kind of strum it together, and then you would kind of see very distinctly the sound of strumming of the blade, or with just rubber bands. This is another very fascinating aspect of physics in terms of sound, which is a type of energy. I'm hoping to meet you soon, and sooner, probably in less than a week's time or so, where I'll be talking about I think heat energy, and I think there's just one more unit before we wrap up. I think that's on electronics, before we wrap up really the course for the class 8, which was really the original objective of starting to do these videos. Well, it's been a pleasure talking to you. There's been, of course, a lag from my end, but I do hope to make up in the next few weeks to complete the assignment that I have taken for myself to cover the entire syllabus of class 8 in a series of lectures. Thank you for the feedback that I've been receiving, and I hope that you continue to enjoy these videos as much as I enjoy making them and bringing them up to you. Thank you guys, and bye.